Bismillahirrahmanirrahim. Hello everyone. In this video tutorial, I'm going to show you how to model, analyze, and design concentrically steel brass frame in ABAQUS software. If you have an experimental data, you can simulate and compare your results. If you don't know, and for designing purpose, you can follow this procedure to design. This is an example. I already modeled this in ETAP software. This is the column, which is 300 by 300, 20 by 20 web and flange sizes. And the beam is 400. The length is 4,000, which we got about 400 millimeters height of the beam by 300, 15, 12. 15 the web flange and 12 the web. Using box section or HSS section 160 by 88. And the material using FY50 grade 50, which has about 200,000 megapascal, modulus velocity 0.3 Poisson ratio, and the yield strength is 345 megapascal, and the ultimate strength is 450 or 48 megapascals. So the strain of this material is about 25%. So this was the information about this model. We are going to model in ABAQUS software. So we are going to the part. We already have this parts, which is 1, 2, 3, 4, 5, 7 parts. So each part, sample like beam columns has same procedure. I'm going to show you. We want to column. The column is 300 by 300 and 20 by 20. So we can use solid elements and we can also use shell elements. If we have some nut bolt connection, then we better use solid elements, and otherwise if it's a weld connection, then you can use shell elements. So I go shell elements and take it's already exists because I'm going to dash point 1, and here I'm going to draw from this point to this point, and again from this point to this point. I'm going to measure the top is 4, we require 300, and it automatically adjusts it for both sides, and this is 300 millimeters. So I'm going to use this command, translate. I take a copy of the top flange, bring it to bottom. Now the cross section is completed. We are going to give the length. So the length is from center to center 3,000. So we extend this to 3,200 millimeters. 3,200. So this is the column. The next is going to draw our stiffener. So the stiffener is welcome to the top of the columns. It be a planar shape, going to call stiffener. It's already exist, so I'm going to dash 1, a rectangle. I'm going to use the size is 3 by 300 millimeters, so it's 300, and this should be 300. So this is the stiffener, and the next is going to define materials. In here I have defined the materials. If you don't have this kind of material in your library, if I go to the my library, in my library here I have different material, so I already saved in my library. If you don't have, then you can go to the here, create a new material. This is called steel. From here you can choose the elastic, which is 200,000 megapascal, and portion ratio is 0.3. And for plasticities, here we can get the plasticity of this material. Here is copy with the L in this L string will be 0. So we extend one more row, and here is the ultimate string. Copy and paste. So the elongation of this grid 50 is 25%. I will give 25%, 0.5. It's called steel is already exists, so I'm going to steel 1. So the material is defined. Now we are going to define one cross section for stiffener and 1 and 2 for columns. So I'm going to use called stiff plate, and this is shell element homogeneous. This is actually the beam. If we go to here, beam, which is going to be beam here, it has about flanges 50 millimeters. So the stiffener on the top of the column should be 15, same as the beam flanges. So the material using is steel 1. Okay, and we can assign this to our, we already have, but it's called SP we given. And next we're going to define called column TF. Column TF means thickness of flange. So the thickness of flange is 20 millimeters. We have steel 1 and one more. It's called column TW, with thickness of web. The same is 20 millimeters using this is the we end the column without applying adding materials. So assigning material, here is the web. We said column thickness of web. So okay, and now select all the flange area, because in the beam it's different, so we should follow this procedure to assign materials, and it's called column TF. So the material is applied, so we don't have anything here else, so go to the assembly. So we already have this in a previous example. I'm going to delete this. I'm not going to delete this, I'm going to hide, because it will take so much time to assemble again. Here is called SB1. So I'm going to steel brass frame we had. I'm going to remove it, so it's gone. So the thing is, the only complex part is that arranging this brass in a correct angles. So you should have we have this height and we have this length, and we should get this angles. So this angle is important to arrange. So according my calculation is about 453.5 degrees. So quickly I'm going to add the columns, so that column which we had, and I'm going to rotate this So take this point and take this point, it will stand, and next select and take this point and take this point, it will rotate to 90 degrees. So I'm going to shift or move to the this sorry take this point to the 0, so the center of coordinate here is. And next we want to bring the one of the brass which is going to rotate. I'm going to show you how we can rotate the brass. So we already have brass frame here. Here is, and I'm going to rotate, take this, but before this I'm going to bring this bottom plate, so bottom gasket. So bottom gasket, I'm going to take this bottom gasket here from this point to this point here, and the next is going to rotate this, taking this point to this point, rotate to these angles. Good. Here is drawing some coordinates, some point here. I'm going to select this to here, and the next thing is I'm going to draw one point in the same in this location. So now let's see here, I'm going to draw here between this to center to center. Now we already determined that angle is 53.5, so you can calculate, because we have height and length and we get the angles. And also we can measure here, we can also measure here angle. So we have three options: face, curve, and 3 point. You can take this point, this point, and this point, this point, this point, this point, center. So I'm gonna rotate, taking this rotate, select, no, it was actually, sorry, going to rotate, select this, and taking this point, and now here is the angle. If it's 90, it will be back. So I'm going to give it its positive turn in this direction. If I give negative, it will give. So I'm going to give negative 53.5. Yes, exactly what we got is the same area. So now I'm going to take this point, select, take this point, and move to this point. Now exactly it comes to the center of these elements. So center of this element. The next is we want to bring the beams and also the gasket plates, and it will totally it will come to the center of this. It's better to bring the beam. So this is beam, and I'm going to rotate this beam. I'm going to rotate from this point to this point, turn like this and move in this point here. And the next is going to bring the gasket plate, and here is the gasket plate. I'm going to shift, take the center of this gasket plate is depends to your project, but for me it's 400 by 800. So now I'm going to bring to this to be the center of this beam. How is it? So correct what we have to do. So it's concentrically in once it will intersect in one center line here. So the same, you will bring other parts and also add, then you use this merge and merge all the beam columns. So I don't want this because I already have. The next part is I'm going to add my holiday project here. So holiday project here. So I already did. And the next is going to setup step. Sorry, step. Uh, I can delete this step. I can delete this step and creating a new step we call cyclic or anything you want. I want quiz I. I'm going to use push pull instead of that. So static. So the total time is about 1500 seconds. For if we take 5000 for second, we can get a better results. How we can get, so we have these parameters, and this parameter should be defined by 1500. Sorry, this the number should define. Here is we have 17 numbers. The total point is 70 point here steps. So this steps should define by this 550,000 should define by 70 steps. So now each step will require this. So now we give the first 0 and the second is this one and twice, and it become double 3, and to reach this number we have create push pull and cyclic, and the time is 1500 seconds. We want to turn on and turn on the non-linear geometries, and we check this to stabilize our analysis because the structure will not abort. So good that here we can give about 10,000 as much as you want, and here be 0.5 I give, and for the minimum increment I give 1 e minus 15, very large small number, and the maximum can be about 10. So this is the step, and next we're going to edit our step using all models, using this every x steps which one, and using the output approximate time and all that pre-defaults. And next here I'm going to create a set. Here's a set actually already removed. But before I'm going to here the same. This is called create data point offset from. I'm selecting this point and I'm going to offset a number which is the loading application. Horizontal loading location should be about 200 millimeters, 250 out of this location. Here I'm giving this data, and this is x direction, and I'm going to exactly give 2 minus 250, 0 and 0. So here is a point, and I'm going to tool reference point, giving a reference point here. So, and the next we have the set. In this set I'm going to display in this reference point might be my displacement point. Here is the output I'm going to create a specific output called RF, which is base share. Base share in the single story is same with the top of them, and I'm going to use U1. The same here. Domain is seat, setting for seat and displacement, and for frequency we're going to hx, which is 1, and the result should be approximate. If it's come 0.9, it should count 2, or, and here we select the displacement U1 or F1, and here is U1. Okay, so now the output is the history output is fixed, and the next is going to the interaction. So we want the law should apply it here because it's not in the structure, but it's a little out of the structure. So we have actuators, so the loading is a little different. You can see. We have one. Going to edit, that's coupling. I can delete this. Sorry, I'm going to delete this, and I'm going to create a new coupling, hope 1, and it's required to have a set number to see this point and surface. Now we're going to select this surface. Select the purple colors, top and dynamic. Okay, so this is set, the loading area, and the next is load. So the load is, we have a displacement load here, and also we have boundary condition here. So we want to, this is base, is an end properties, it's already giving, and this is the U2, which is this area. We want to prevent the Z direction restraint because there is a 3D structure and also some stiffener, so we want to restrain the U3. And the next one is which is called push pull in the push pull area. So we want to select our displacement area, this point, and it's in direction 1, which is 1. This is the ramp. We already giving this these two column data as a amplitude. Okay, now everything is done for next mesh. So we have meshed, we can use mesh. So if I go to delete the mesh, if I go to here, delete the mesh, sorry, it's been here. If I go to delete the mesh, so this is deleted mesh, and I'm going to again, here is, I used a 60mm size of mesh. You can as much as you want. If you use fine mesh, that's better. Coarse mesh will not giving accurate results. I use 60mm, which is quite fine. And also you can use the element. So quad, I prefer to use free quad dominated, which is a little if I use quad, that will maybe abort in some area. If I do, it's also okay. But going to here for meshing, I'm going to mesh, yes. So for quad area, yes, I should. It's already meshed, but for quad area, some part the meshing is not right, and maybe if we want to check, then we can check if it's not problem, and here we can see highlight, and there is actually not any error. So this quad is also better. And next is job. So job, we already have one job, and I'm going to select this job called push pull. You can change your CPUs, but I will keep it. I will keep it as a default. Now I can give submit. So it should start running, and we can go to check it's successfully the submit is successfully completed. We go see here is not this one and this one running monitor. Here is starting the working is work well. Okay, and we are going to talk about this parts which is already done. So in monitor we can see, yeah, in monitor it's completed 1500 steps. So this is the loop which is we submitted in this time 1 o'clock 1:53, and it's completed on 2:20. So it's almost take about half hours to complete. So now we gonna monitor again our push pull is 210. It's quite going fast, and we're gonna check the results. This is the results. So in the first we have largest stress in the brass, and we can check some active yield parts. So still there is not yield. So we can wait for a while. I will pause the video, and about maybe half hours we will return back. In step 400 we got yielding in the brass system, because the brass system will bear the horizontal force and resist the earthquake forces. So it will first yield. So after the yield, it will go to buckling. If we go to the deformation or deformation in U3, we can see the buckling is began in the U3 in the brass elements. So it take time about maybe half hours or 30 minutes. So we can check some another results output here. We already had this 2 point, one is reaction force, one displacement, and we can call save as okay, and this is the hysteresis behavior, and we can go to back to this and use operation using we already in previous result we have delete, we go to delete and we go to back output, and here is reaction force, and here is displacement save as, and here is the operation. We use combine xy, and this is displacement in the x direction is y. So plot, we got this 1 cycle, this is 2, and this is the first is complete and the second is going on. So this is like the we got this number. So we have the data here. We can copy this data. We can copy this data. So copy, and here is the I have draw hysteresis. You can paste here, paste, and I used draft. And if we use draft, you can insert one more column, and here is I can write, give this to copy, this to copy, Control V. This is draft. Draft is equal. Here is the equations, the displacement divided by height. It's equal the displacement divided by height. Height is the 3000 millimeters, and this is newtons, and it should be equal this divided by 1000. So now we can extend. Here we got 0 because we still it's not completed. So then we can add a graph. So this is our graph. So this is the hysteresis graph. So about 0.02%. For this, we have in this 0.2% is almost here we can see maximum displacement is about 20 millimeters, such as, or 10 millimeters. Yeah, it's about 7 millimeters or 10 millimeters. So in this displacement, in this displacement, we got yield active yield in the brass system. Now it's about 500. So some other yields began in the top of the beam columns connection. So if we see further, now it's going to buckle larger. So maybe we cannot wait for this, and finally we got these results. We got these results from the previous. If you wait for a long time, about 1 hour or 40 minutes, then you will get that complete, and then you can draw your result like this. And if you have experiment, then you can compare the results. So if you have any question, you can put in the link, and I will find time to answer your question. And this was the end of our tutorial. Next time we will do steel brassed frame with eccentrically brass. So thank you for watching. See you next time.